think this is now working. It's been a long time since I've used the YouTube live streaming feature, but I have students who need to review for a test, so I have this study guide here, and we will get into that. Let's need to make you link. I will now send this to my student. Link. I will now send this to my student. Link. I will now send this to my student. I don't type very fast. So, to any of my students who are watching a recording of this, since no one is currently watching, this was my old YouTube channel when I used to make Minecraft videos, and it would be really nice to get back to making Minecraft videos at some point. I have a nephew who is just old enough to start, like, maybe I'll get back. Lots of things have happened, but we're using the channel today to do a test review for this this study guide. Actually, I have a few study guides available, and yeah, I figured this would be the best solution because my car broke down today and I couldn't get to it. And my students need me to help them with getting ready for the so here we go. So maybe like this. Maybe I'll read it and then pull. So we want to, according to the rational roots theorem, write down the possible roots for the following polynomial function. This function. Okay. So the way the rational roots theorem works is you take all of the factors of the constant, that's -4, and you divide them by all of the factors of the leading coefficient, that's 6. So let's I used to have a tablet that I would write on in my live stream, and unfortunately that has gone the way of all the earth, and it doesn't work anymore. But that might be a little small. That looks okay. So first we're going to write out all of the factors of our constant. So that'll be 1 and -1, 2 and -2, and 4 and -4. Then we're going to divide each of those by the factors of our leading coefficient. So the factors of the leading coefficient are 1, 2, 3, and 6. You might be wondering, well, why did I do positive and negatives for the constant term, and I'm only doing positives for the leading coefficient? The reason for that is I don't need to write down any root more than once. But I have to write down all of them. They can come in a positive form and they can come in a negative form. But if I take a number and divide it by a second number, The only possible outcomes are I either have the same sign and I get positive, or I have different signs and I get a negative. So this this 1 here represents having the same sign as the denominator. This -1 represents having the opposite sign of the denominator. And that gets me all of my combinations. I don't need to worry about the... I could have picked the... I could write the whole thing out and then just delete all the duplicates, but I might as well just not write them in the first place. Anyway, 1 divided by 2 is a half. I might have done well to have made the columns a little wider. This. And since it's early enough in the live stream, maybe we will this, delete it, make my columns bigger so that I have room to go down. So we have 1, space, -1, space, negative 2, -2, 4, and -4. After that, I'm going to create a new line. Then I have 1/2, -1/2, and then 2 over 2 is 1. And I can write 1, and I can write -1, and I can do that, but as I said, I don't need to have duplicates on my list. I'm just creating a list of the possible roots. I might as well just ignore duplicates. Down 1/3 is a new value to my list. -1/3 is also a new value. 2/3, -2/3, 4/3, and -4/3. These are all possible roots. 1/6, -1/6, and then 2/6 would be the next one. But 2/6 is equal to 1/3, and 1/3 is already on the list, so I don't need it. Same thing with 4/6. 20 THs. 4/6 is also going to be 2/3 again, and so I don't need to write that. Here are all of the roots of this polynomial. So, oh, and so anyone in the chat, which I have someone in the chat right, feel free to ask questions, and I will answer them to the best of my ability. Like there's some sort of problem. But it says stream health is good. Hopefully that's good enough. Oh, are you not able to see? I've been writing notes. Yeah, it looks like you're able to. Okay. So I have these. This is the answer to the first question. The rational roots theorem allows us to create this number system that I have here. So that's how we do. The next question on the list is, according to Descartes' rule of signs, how many positive roots and how many negative roots could the following function have? It's the same polynomial as before. So, Descartes' rule of signs counts sign switches. What we mean by that, let me unhighlight a little bit. So right now we have a positive, that's the 6x to the 6th, and then a positive, that's the x to the 5th. Then we have a negative 4x to the 4th, a positive 13x to the 3, a negative 34x squared, a positive 22x, and a negative 4. So these are the signs of our polynomial in standard form. Descartes' rule of signs applies to the times that we change sign. So, for instance, here we switch from positive to negative. Here we switch from negative to positive. So, usually we do an arc. And I have here 5 sign switches. So, Descartes' rule of signs says that the number of positive roots is the number of sign switches minus an even number. So 5 minus 0, 0 is an even number, is 5. 5 minus 2 is 3. 5 minus 4 is 1. And if I try and do any other positive numbers, any other non-negative even numbers, then I get a number that doesn't. Basically, I start with the number of sign switches, which in this case was 5, and I'm going to count down by 2 until I can't anymore. 5 to 3, 3 to 1, 1 goes to negative 1. We can't have a negative number of things. So the number of positive roots is either 5 or 3 or 1. Now, the first misconception about Descartes' rule of signs is it does not tell you what the roots are. The next misconception is it does not tell you how many roots. It tells you these are the possible number of positive roots. So it's not that there are 5 positive roots, it's that there could be. Or there could be 3, or there could be 1, but no other possibilities exist. So, moving on. Well, we also want to have how many negative roots? Well, Descartes' law of signs only applies to positive roots. It only works on positive roots. But when we plug negative x into a function, we flip the graph across the y-axis. So whatever our function was, our function, and here's our axis. Whatever our function was, we can plug negative x into it, and that will flip horizontally. Like, that did not do what I had hoped it would. I was hoping to be able to select it. Flips the whole thing. I don't want to flip the thing, I just want to flip the selection. Well, that would have been neat. We could have done that. I don't know how to do that. Okay. It would flip it. Oh, we can. There we go. So it would flip it across the y-axis like that. So all of the roots that would have been negative, say this was a root here, maybe. This were a root here. Then after the reflection, it would be a root here. It was a negative root, but after the flip, it becomes a positive root. And then we could use Descartes' rule of signs on this flipped graph to find the positive roots of the flipped graph, which would then be the negative roots of the original graph. Okay. Delete that, give us some space. So we will now do the flip on this here by plugging negative. Can't copy text. Okay. So we have 6x to the 6th plus x to the 5th minus 4x to the 4th, 13x third minus 34x squared plus 22x minus 4. And if we plug negative x into these spots here, so we plug negative x into the function, that will flip it. All we have to do is take, I'm not using, so if we do this, we will notice that a negative x to an even power is just the negative signs all cancel. So when I go through this and I plug in negative x, the first thing I notice is that when I have an even number of x's, like this 6 here, then, well, all of the negative signs cancel, and I just get back what I started. On the other hand, if I have an odd power like this 5, then I have an odd number of negative sides. An even number of them will cancel, but the last one will not. And that will flip the sign of that term. If it was positive, it becomes negative. If it were negative, it becomes positive. So all of these even powers, their signs stay the same. All of the odd ones, we will flip the sign when we plug in negative x. So this is what we get after we have flipped the signs of the function. And if we do the same thing we did before, we get the first term is positive, the second term is negative, the third one is negative, the fourth one is negative, the fifth one is negative, the sixth one is negative, and the last one is negative. And so the number of sign switches becomes just the one sign switch. So that means that Descartes' law of signs says that there are either the number of positive roots is 5 or 3, 4, and the number of negative roots is just 1 for this function. Okay. So that's 20 points out of 80 right there. That's a quarter of the test, or at least the quarter of the last semester version of the test, because this was spring of 2024. Now we need to find the roots. This is where it gets longer. So we have this sieve up here. We can actually, might be a good idea to copy and paste that. Okay, so we have this, and we want to check all of the numbers in our sieve that we need to factor this polynomial. There we go. Okay, so we are going to do synthetic division. We're going to start with the non-fractions, because those will be easier for us to do. We're going to take the coefficients from our function, which are 6, -1, -4. And we need the original function. So 6, 1, -4, 13, -34, 22, and -4. And we're going to divide them by 1. So, with synthetic division, the way that it works is I'm going to pull this number down, 6, and then I'm going to multiply it by the number over here, which is the 1. 6 times 1 is 6. Then I go up here, and I have 6 plus 1 is 7. 1 times 7 is 7. 7 minus 4 is 3. 13 plus 3 is 16. 16 times 1 is 16. 16 minus 34 is -18. We have 18 times 1 is, or -18 times 1 is -18. 22 minus 18 is 4. 4 times 1 is 4. -4 plus 4 is 0. And this 0 says that we were able to divide with no remainder. The last number here on the bottom row represents the remainder. If we get a 0 there, that means that we found a divisor that divides evenly, which means that we found a factor of the polynomial. We found a root of the polynomial. So let's make a list of roots over here. Here's our list of roots. And the first number we add is 1. 1 is a root. Now, this this list of numbers here is the factored polynomial. So these were the coefficients of the original polynomial. These are the coefficients of the polynomial we get after factoring out this root. So we factor this polynomial using the same method that we used on the other one, which is the rational roots theorem and the law of sines and synthetic division. However, we already created our number. All we have to do is check to see, do the things on this number sieve still apply? So we check 1, -1, 2, -2, 4, -4. Are those factors of the constant here? The answer is yes. So those are all still good, which means the numbers in those columns are mostly good. We also have to check to see, are these numbers here factors of the leading coefficient? And the answer is yes. 1, 2, 3, and 6 are all factors of 6. So this time we weren't able to cancel anything from the number sieve, but sometimes we can. We did find a positive root, so we know that. Where did I put it? I said, oh, we have 5, 3, and 1. These are the number of positive roots, 1, 3, and 5. We found 1. That might be all of them, but there might be 2 more, or there might be 4 more. On the other hand, there's only 1 negative root. We know that there's 1, 2, 3, or 5 positive roots, and there's only 1 negative root. Okay, so let's go on to the next round of polynomial long division. I'm going to check to see if 1 is a double root by plugging it in again and doing the same process. Bring down the 6. Oh, I wonder if I can do this. Oh yeah, bring down the 6. 6 times 1 is 6. 7 plus 6 is 13. 13 times 1 is 13. 13 plus 3 is 16. 16 plus 16 is 32. Should bring this. 16 plus 16 is 32. 32 times 1 is 32. 32 minus 18 is 14. 14 plus 4 is 18. And we have no factor. Our remainder is 18. Every time that you have a successful synthetic division, you will have 1 fewer columns than you had before. So this -440 column, that was when we had a degree 6 polynomial. This is a degree 5 polynomial, so it ends on this column for 14, 18. And that tells us that 1 is not a multiple root. That's not. 1 is not a multiple root. We don't have to check it anymore. When you have a failure, you go back to the last row of the last synthetic division that worked. That is going to be this one here. This row is going to be copied. And we're going to try again with that with the next root. So let's copy this row. And let's start with well, let's go to -2. Sorry, let's go to -1. We'll do -1 next. So we bring down the 6. here. 6 times -1 is -6, which 7 minus 6 gives us 1. So 1 times -1 is -1. -1 plus 3 is 2. So 2 times -1 is -2. 16 minus 2 is 14. 14 times -1 is -14. -14 plus 18 is, sorry, -14 plus -18 is -32. Times 1 is +32. 4 plus 32 is 36. So that one didn't work either. So that tells us that -1 is not a root of this polynomial. Okay, we're going to do this again. Again, we're going to copy the most recent row that worked, this one, set up our synthetic division again. Let's try 2. So we're going to bring down the 6. Then we are going to do 2 times 6 is 12. And then 12 plus 7 is 19. 19 times 2 is 38. 38 plus 3 is 41. 41 times 2 is 82. 82 plus 16 is 98. 98 times 2 is 196. 196 minus 18 is 170 something. Let's 178. And then 2 times that is going to be big. It's like 360 something. 356, I think. We don't really need to know the exact value on that because that plus 4 is going to be positive. We have 360, I think is what we get. So this here introduces one of our other tools. So we have an upper bound theorem on synthetic division. That upper bound theorem works like this. If you're dividing by a positive, and if after doing synthetic division your bottom row is all positive, that means that this number here is bigger than or equal to all of the other roots of the polynomial, all of the other real roots of the polynomial. So since this is positive and since this is also positive, we know that 2 is bigger than or equal to all of the roots. So we can cross off all of the roots that are bigger than 2. So 4 is bigger than 2. Let's change our color back to black. And I guess the other numbers are not bigger than positive. But we did get to cross that one off for free. We get to cross off 2 for free. Well, 2 because we checked it actually. Okay. So we didn't get one that worked, so we're going to start again with the last row that we did divide. We go to the next Okay, so the next root we'll check will be -2. Okay, so we bring down the 6. 6 times -2 is -12. 7 minus 12 is going to be -5. Times 2 is +10. Plus 3 is 13. Times -2 is -26. Plus 16 gives us -10. Times -2 gives us +20. Minus 18 gives us 2. Times -2 gives us -4. And 4 minus 4 is 0. So we found another root that works. Let's add that to our list. We have -2 as our next root that works. Okay. And we notice that the constant changed. Now it says 2 instead of 4. So that means we're going to go back to our number sieve and cross off the things that are not factors of 2. So on the top row. So on the top row, -4 is not a factor of 2. So we get rid of it. But that also means that we get rid of everything in that column because the numerator is not a factor of 2. We also can get rid of this one for the same reason. Also, we know that there's only one negative root by the Descartes' law of signs. So we change the size of that tool. I'll use the here. We have one negative root, and we found it. So what that means is we can now X out all of the other negatives because there are no more. So we're getting pretty, we're looking pretty good on our number sieve. We only have 4 more terms to look at. Not terms, 4 more potential roots to look at. So let's keep going. Since we had a successful one, meaning that our root was, our remainder was 0, we get to continue with this smaller polynomial. And we might as well check a half. So we pull down a 6. 6 times a half is 3. 3 minus 5 is -2. -2 times a half is -1. 13 minus 1 is 12. 12 times a half is 6. 10 minus, well, 6 minus 10 is -4. Half of -4 is -2. And 2 plus 2 is 0. So that was successful. Okay. Now, if you notice this this factor here went back up to 4, we do not have to add things to the number sieve. If we made the number sieve correctly to begin with, then we never have to add things to it. We'll just delete. But the reason that it went up was because we divided by a fraction that was less than 1. And that often will make the constant term go higher. So it's just an unfortunate thing. But so that's why I like to do the top row of these first. That's one of the 2 reasons. One is that I'd rather procrastinate using fractions until later. But even if we have to use fractions, it's beneficial to go across the top row because that will not increase our constant. Okay, so let's go to the next. Let's check the next one. Okay, so we might have a double root with 1/2. This is not ruled out as being a multiple, like it could be a multiple root. We haven't ruled that out. So let's try 1/2 again. So we bring down the 6. We do 6 times 1/2 is 3. And then we do 3 minus 2 is 1. 1/2 of 1 is 1/2. Plus 12 gets us 12 and 1/2. And 1/2 of that is going to be 6 plus 1/4. And adding that to -4 is not 0. We don't actually have to figure out what that number is, although it is, I guess, 2.25. We don't need to figure out what that is. All we need to know is that it's not 0, so therefore this was not a root. It was a root one time, but it's not a multiple. So go back up here, and we cross out 1/2. 1/3 looks like the next root for us, so let's use that. We will go back to the previous row that worked for us. This one, copy it. And let's do our static division line. We actually don't need to include that 0. I can delete that one. Okay. Let's try 1/3. We bring down the 6. 6 times 1/3 is 2. 2 minus 2 is 0. 0 plus 12 is 12. Times 1/3 is 4. 4 minus 4 is 0. Okay, so that worked. And at this point, when I look at this, I see this is a quadratic. This here. This translates to 6x squared plus 0x plus 12. And if I want to factor this, I can. I know that I can divide both terms by 0. I can divide both terms by 6. So I get x squared plus 2 equals 0. And from there, I can use whatever way I would like to solve this. Quadratic formula, completing the square, whatever I would like. I'm just going to subtract 2 from both sides. And then take the square root. You say, oh, we can't take a square root of -2. Well, in college algebra, we do allow complex numbers some of the time, and this is one of those times. So we know the square root of -2. We can take out an I. We get I times the square root of +2. Also, we do know that there is a positive and a negative root when we solve when we take the square root to solve for x, we get both the positive root and the negative root. So we're going to get both a positive I square root 2 and negative. So I will write that this way. We have I square root 2 or negative I square root 2. We have square root negative 2 or negative square root of negative. So, oh, and I guess we forgot to write all of these down. We have a root is 1. Got that here, 1. Then the next root we got was here, negative 2. And then a half worked. And then looks like a half was a double root. As we, no, it wasn't a double root. So first root we found was we have this 0 here, which means 1 was a root. Then we have this 0 here, which means negative 2 is a root. This 0 here means half was a root. And then, are we missing a root somewhere? This means a half. 1, negative 2. Negative 2 half. Then we have I square root 2 and negative 2. Where's the last root? Only 5 of them. 5. Oh, and 1/3 up here. There's the 6th. We know that there are 6 roots because the degree of the polynomial was 6. Oh, looking over here, the degree of the polynomial is 6. This is the highest exponent on any of the terms, so therefore it is the degree of the polynomial. And the number of roots when you factor in the complex plane is always going to be equal to the degree. You can have less roots if you only allow real roots, but you'll have exactly the degree's number of roots if you factor all the way into complex numbers. So, hope that that was helpful. And I guess if you have any other questions, please let me know and I'll get to them for the test tomorrow. So, have a great day. That was a good recording for you, and I will see you in class tomorrow when my car is fixed.